The sun was angry, not in the way you might imagine, with sudden bursts of rage that flare and fade, but with a slow, burning fury that had been building for years. Solar cycle 25 had begun quietly in December 2019, and at first scientists predicted it would be a gentle thing, a relatively weak cycle that would pass without much fanfare. They were wrong, spectacularly wrong. By August 2024, sunspot counts reached heights not seen in 23 years. The solar surface became a roiling cauldron of magnetic chaos, twisting and writhing with energies that defied the conservative forecasts. Then in October 2024 came the official announcement that sent ripples through the scientific community. Solar maximum had arrived. This was not supposed to happen with such intensity. This was not supposed to be so violent. Yet there it was, undeniable and fierce, crowned by an X 9.0 flare that tore through space with the power of billions of nuclear bombs. Solar cycle 25 had exceeded every prediction, and it showed no signs of calming down. The cycle was expected to continue its rampage until around 2030, meaning we were only halfway through this cosmic storm. For those who monitor space weather, the implications were clear and chilling. This was no longer about isolated incidents or freak events. This was the new normal. High-impact geospace hazards were now the baseline operational environment for every satellite, every power grid, every communication system on Earth. We had entered an era where the sun itself had become a persistent threat. Then came the sequence. 4 X-class flares in rapid succession, each one a monster in its own right: X 1.7, X 1.2, X 5.1, X 4.0. They erupted from a single active region designated AR 4274, a sprawling magnetic battlefield in the solar surface so complex that it seemed almost deliberately engineered for destruction. The flares did not come randomly spaced over weeks or months. They came fast, one after another, like hammer blows against a shield of Earth's magnetosphere. The X 5.1 flare peaked on November 11, 2025. It was the strongest solar flare recorded all year, a brilliant, catastrophic explosion of electromagnetic radiation that reached Earth in just 8 minutes. But the real danger was not the light. It was what followed. The coronal mass ejection, the CMEs, a billion-ton cloud of superheated plasma hurled into space at millions of kilometers per hour, aimed directly at our planet. Here is where the story becomes terrifying in its physics. A single CME striking Earth can cause significant disruption, but this was not a single strike. The major geo-effective CMEs from the first 3 flares were already on their way, already crossing the void between Sun and Earth. The forecast models showed something unprecedented. The CMEs would arrive in quick succession, each one slamming into a magnetosphere already reeling from the previous impact. The second CME would not hit a stable, recovered magnetic field. It would hit a field that was stressed, compressed, and vulnerable. This is the nightmare scenario for space weather forecasters. When successive CMEs collide with Earth's magnetosphere in rapid sequence, the effects do not simply add together. They multiply, they compound. The magnetic field, already weakened and distorted by the first impact, cannot recover before the second blow arrives. The result is a geomagnetic storm of extreme severity, a chaotic maelstrom of electromagnetic turbulence that engulfs the entire near-Earth environment. The official forecast called it a severe G4 geomagnetic storm, just one step below the maximum G5 classification. But those who remembered the great storms of the past knew better. The May 2024 storm had been forecast as G4 and became G5. The legendary Halloween storm of 2003, the same. History had taught a brutal lesson. Well, when the forecast says G4 and the conditions are right, expect G5, and the conditions were very, very right. The key variable, the one that determines whether a CME is a glancing annoyance or a civilization-threatening event, is the interplanetary magnetic field, specifically its north-south component called B sub Z. When the solar wind carries a magnetic field oriented southward, anti-parallel to Earth's own magnetic field, something extraordinary happens. The two fields connect through a process called magnetic reconnection, and suddenly a door opens. Solar wind energy, momentum, and plasma flood directly into the magnetosphere with brutal efficiency. The severity of the storm that followed confirmed what the physicists suspected. The B sub Z component of the incoming CME was strongly and persistently southward. The magnetic coupling was nearly perfect. Energy transfer was maximized. The magnetosphere, that invisible shield generated by Earth's molten iron core, was compressed dramatically, squeezed like a balloon under pressure. The magnetic field lines on the day side collapsed inward, pushed back by the relentless pressure of the solar wind. The evidence of this compression was visible to anyone who looked up. The aurora borealis, normally confined to the Arctic Circle and high-latitude regions, surged southward with astonishing speed. Vivid curtains of green, red, and purple light danced across skies that had never seen them before. Northern lights appeared over North America and Europe, brilliant and eerie. But the truly shocking sightings came from farther south. Nuevo Leon, Mexico, northern Spain. Latitudes near 20 degrees north, regions where the aurora should be physically impossible under normal conditions. This was not beauty. This was a warning. The aurora is not just a light show. It is the visible signature of massive electrical currents flowing through the upper atmosphere, currents driven by the compressed and distorted magnetosphere. And these currents do not stay in the sky. They reach down, penetrating deep into the conductive layers of the Earth's crust, generating what scientists call geomagnetically induced currents, or GICs, during a G4 to G5 storm. These GICs become torrents of electrical energy, flowing through the ground itself, following paths of least resistance through rock, metal, and water. Power grids feel them as surges that can melt transformers. Pipelines corrode under the invisible electrochemical assault. And deep below, in the high-stress zones where tectonic plates grind and lock, these currents add their energy to faults already loaded to the breaking point. The sheer magnitude of energy transfer during the storm was staggering. The external electromagnetic stress applied to the planet reached levels seen only a handful of times in recorded history. This was the kind of event that makes geophysicists sit up and take notice, because it represents a rare and dangerous convergence. A sun delivering maximum energy, and an Earth magnetosphere accepting it with maximum efficiency. A R4274 was not finished. Even as scientists assessed the damage from the first wave of impacts, the active region continued to churn and twist. On November 14, 2025, at 8:30 UTC, it unleashed its fifth X-class event, an X4.1 flare, later refined to X4.0 in measurements. The persistence was remarkable and deeply unsettling. This was not a single explosive release of pent-up magnetic energy. This was a sustained campaign of solar violence, a region of the sun so fundamentally unstable that it kept finding new ways to explode, but the sun was not acting alone. As AR4274 unleashed its barrage of X-class flares, 3 visitors from the far reaches of space were making their way through the inner solar system comets. Ancient wanderers carrying ice and rock from the beginning of time, following orbital peaks that would bring them dangerously close to the fury of our star. Their presence during this period of extreme solar violence was more than mere coincidence. It was perhaps a piece of a puzzle that scientists were only beginning to understand. The first was Comet A6 Lemmon, officially designated C/2025 A6. This was no fresh newcomer to the solar neighborhood. A6 Lemmon was a dynamically old comet, a long-period traveler that had made this journey many times before across billions of years. Its orbit was well known, and astronomers had calculated its perihelion with precision. November 8, 2025, at a distance of 0.53 astronomical units from the Sun. That is just over half the distance from Earth to the Sun, close enough to feel the full intensity of solar radiation, close enough to begin shedding material in great jets of sublimated ice and dust. The timing was remarkable. A6 Lemmon reached its closest approach to the Sun on November 8th. The major X-class flare sequence from AR4274 began on November 7th and peaked on November 11th. The overlap was precise, almost surgical in its alignment. Then there was Comet T1 Atlas, designated C/2025 T1. This object was near its closest approach to Earth around November 14, 2025, placing it squarely within the inner solar system during the most intense phase of solar activity. T1 Atlas was following its own elliptical path, but like A6 Lemmon, its presence during the flare sequence raised questions about the nature of these cosmic alignments. But the most intriguing visitor was the third, Comet 3, Yeti's I Atlas. The designation alone should tell you everything. 3. Albei means third interstellar object. This was not a native of our solar system. This comet had been born in the disk of material surrounding another star, light years away, forged under conditions utterly alien to anything in our stellar neighborhood. Somehow, through gravitational perturbations or stellar encounters we can only guess at, it had been ejected from its home system and sent hurtling through the galaxy. And now, after thousands or millions of years of travel through the cosmic void, it had arrived here, passing through our solar system at the exact moment when the Sun was at its most violent. The odds of such a convergence seem astronomical, and they are. Interstellar objects are rare. We have only confirmed 3 in all of human history. The first was Oumuamua in 2017, a strange, elongated object that tumbled through the inner solar system and departed before we could study it properly. The second was Comet Borisov in 2019, which behaved more like a traditional comet but still carried the chemical fingerprints of another star's planetary system. And now, 3I Atlas, arriving during solar cycle 25's peak fury. What made 3I Atlas especially fascinating and somewhat unsettling was its behavior. Most comets are predictable. As they approach the Sun, solar heating causes surface ices to sublimate, creating the characteristic coma and tail. The outgassing is usually symmetrical, driven purely by solar radiation. But 3I Atlas was different. Observations revealed something extraordinary. The comet was emitting a refined metal compound never before seen in nature, and it was directing a jet of material specifically toward the Sun. This was not normal cometary behavior. This suggested an active process, something driven by the unique chemical composition of an interstellar object. The nucleus of 3I Atlas likely contained exotic ices, organic compounds, and mineral grains formed under entirely different stellar conditions, exposed to different radiation environments, enriched with isotopes and elements and ratios unknown in our solar system. When these materials began to heat and sublime, the results were unpredictable. Standard solar physics would tell you that solar flares are driven entirely by internal processes within the Sun itself. active regions like AAR4274 form when magnetic flux tubes rise through the convective zone and pierce the photosphere, creating sunspots and complex magnetic topologies. When these magnetic structures become too twisted, too stressed, they snap through a process called a magnetic reconnection, releasing energy in the form of flares and CMEs. This is well understood physics, confirmed by decades of observation and modeling. But what if there is more to the story? What if external factors, previously dismissed as negligible, can play a subtle but critical role? The temporal alignment between the cometary events and the flare sequence demands consideration. A6 Lemmon reached perihelion on November 8th. The first major flare erupted on November 7th. The X5.1 flare, the strongest of the year, occurred on November 11th. T1 Atlas was near closest approach to Earth around November 14th. And through it all, 3 I Atlas was present, releasing its exotic plasma into the solar wind. Consider the physics. A comet, especially an active one near perihelion, is not a passive object. It's surrounded by a coma of gas and dust that can extend for hundreds of thousands of kilometers. This material is ionized by solar radiation, creating a plasma environment. That plasma carries electric currents and generates its own magnetic fields. When this plasma interacts with the solar wind and the sun's global magnetic field, it does not simply vanish. It becomes part of the local electromagnetic environment. For a typical comet, this interaction is negligible on solar scales. The sun is vast, powerful, and utterly dominant. A comet's influence is like a candle next to a bonfire. But 3I Atlas was not a typical comet. Its interstellar origin meant its chemical composition was fundamentally different. Different ice is sublime at different temperatures. Different minerals carry different electrical properties. If the plasma released by 3I Atlas possessed unusual conductivity, unusual magnetic susceptibility, or unusual charge distributions, it could, in theory, interact with the heliospheric current sheet or with the magnetic field lines threading through the solar atmosphere in unexpected ways. The hypothesis is speculative, but not absurd. AR4274 was already in a state of critical instability. Its magnetic structure was twisted, stressed, loaded with energy, and on the verge of eruption. In such a state, even a small external perturbation could act as a trigger, the final push that causes the system to snap. If the plasma from 3I Atlas, carried by the solar wind, somehow influenced the boundary conditions near the active region, it might have provided that trigger. This is not gravitational influence. Comets are far too small to exert meaningful gravitational force on the sun. This is an electromagnetic influence, a subtle modulation of magnetic field topology at the boundary between the solar atmosphere and the interplanetary medium. Such effects would be nearly impossible to detect with current instrumentation, but they are not ruled out by physics. The broader question is whether comets, particularly interstellar comets, can create what might be called a solar activity window, a period during which the sun is more prone to eruption. If the presence of an interstellar object introduces anomalous plasma into the inner heliosphere, and if that plasma can interact with active regions in magnetically complex states, then the answer might be yes. Not as a direct cause, but as a catalyst, a trigger for events that were already primed to occur. This hypothesis requires further study, continuous observation, and rigorous modeling. We need to monitor future interstellar objects as they pass through the solar system. We need to correlate their presence with solar activity. We need to analyze the plasma they release, measure its properties, and simulate its interaction with the solar magnetic field. The data is limited, but the question is profound. Can the cosmos itself, through the arrival of wanderers from distant stars, influence the behavior of our own sun? The answer may redefine our understanding of space weather and the interconnectedness of the galaxy. For now, the alignment stands as an anomaly, a mystery wrapped in fire and ice, demanding answers that science is only beginning to seek. While scientists debated the mysterious alignment of comets and solar fury, a more immediate question demanded answers. Where was all of this energy going? The X4.0 flare that erupted on November 14th had launched yet another coronal mass ejection into space, and the question on everyone's mind was simple and terrifying. Would it hit us again? The answer required sophisticated modeling, the kind of physics that turns observational data into predictions of cosmic trajectories. When a coronal mass ejection erupts from the sun, it does not travel in a straight line like a bullet. It expands, it distorts, it interacts with the ambient solar wind. Its path curves and shifts based on magnetic pressures, density gradients, and the invisible architecture of the heliosphere. Predicting where a coronal mass ejection will go and when it will arrive is one of the grand challenges of space weather forecasting. The primary tool for this task is a model called Wang-Shili-Arge-Enlil, operated by the National Oceanic and Atmospheric Administration's Space Weather Prediction Center. Wang-Shili-Arge-Enlil takes coronagraph images from spacecraft like Solar and Heliospheric Observatory and Solar Terrestrial Relations Observatory and uses them to construct a three-dimensional representation of the coronal mass ejection. The model treats the ejection as a cone expanding outward from the sun, with properties like speed, direction, and angular width estimated from the observations. Then it simulates the coronal mass ejection's journey through the solar wind, accounting for how the ejection slows down or speeds up as it encounters regions of varying density and magnetic field strength. For the X4.0 event, the modeling revealed something both relieving and fascinating. The coronal mass ejection was mostly directed away from Earth. The trajectory analysis from both the National Oceanic and Atmospheric Administration and the European Space Agency's European Heliospheric Forecasting Information Asset Model showed that the bulk of the plasma cloud would miss our planet. We would receive only a glancing blow, a fast shock wave at the edge of the coronal mass ejection structure, but not the dense magnetic core that drives the most severe geomagnetic storms. This was critical information. A glancing blow means limited energy transfer. The magnetosphere would feel a jolt, a rapid compression followed by oscillations, but nothing like the sustained bombardment that produces G4 or G5 conditions. The forecast called for geomagnetic activity, reaching minor storm at G1 to moderate storm, G2 levels, depending on the orientation of the interplanetary magnetic field within that shockwave. If the B sub Z component happened to be southward at the moment of impact, we might see enhanced auroral displays at high latitudes and minor disruptions to satellite operations. If it was northward, the event might pass with barely a ripple. For power grid operators, satellite controllers, and communication networks still recovering from the previous week's onslaught, this forecast was a reprieve. It meant time to assess damage, repair systems, and prepare for the next inevitable wave. Because Solar Cycle 25 was not finished, the cycle was expected to remain active until around 2030, meaning years more of this elevated threat level, years more of coronal mass ejections, and X-class flares, and geomagnetic storms that could strike with little warning. But while Earth would be spared this time, the coronal mass ejection was not going nowhere. Trajectory modeling showed that the plasma cloud was heading in a very specific direction, toward the interstellar Comet 3 Zobadirbide I NATLAS, both National Oceanic and Atmospheric Administration and Solar Terrestrial Relations Observatory. A data indicated that the coronal mass ejection would intercept the comet's orbit, and early National Aeronautics and Space Administration forecasts had explicitly predicted a direct collision between the billion-ton cloud of solar plasma and the ancient visitor from another star. This was an event of extraordinary scientific value. Coronal mass ejection impacts on comets are rare and difficult to observe. Most comets are too distant or too faint for detailed study, and coronal mass ejections themselves are transient, chaotic structures that dissipate as they move outward through the heliosphere. But 3I Atlas was relatively close, well observed, when about to be struck by one of the most energetic coronal mass ejections of the year. What happens when a coronal mass ejection hits a comet? The physics is violent and complex. A coronal mass ejection is not just a cloud of particles, it is a magnetized plasma structure, a magnetic flux rope carrying entangled field lines and electric currents. When this structure collides with the comet's coma, the neutral gas surrounding the nucleus, the solar wind plasma ionizes that gas almost instantly. The newly created ions are swept up by the coronal mass ejection's magnetic field and accelerated to high speeds, creating shock waves and turbulence. For a typical solar system comet, this interaction causes the tail to brighten and the coma to expand as outgassing rates increase. The sudden influx of energy heats the nucleus, boiling off more ice and releasing jets of material. Sometimes the tail disconnects entirely, severed by magnetic reconnection events within the coronal mass ejection structure, and a new tail grows in its place over the following hours. But 3I Atlas was not a typical comet. Its interstellar origin meant its composition was fundamentally alien. The ice might be enriched with carbon monoxide, methanol, or nitrogen compounds in ratios never seen in solar system objects. The dust grains might contain minerals formed in the atmosphere of a red giant star, or the remnants of a supernova explosion. The nucleus might be porous, fragile, held together by exotic chemistry that does not respond to solar heating in predictable ways. When the coronal mass ejection struck, scientists expected one of several outcomes. Best case, the comet would brighten dramatically as the impact energy vaporized surface ices, creating a temporary outburst visible to ground-based telescopes. The spectral analysis of that outburst would reveal the chemical fingerprints of interstellar material, providing clues about the environment where the comet was born. Worst case, the comet would fragment, torn apart by thermal stress and mechanical shock, scattering its nucleus into a debris field that would dissipate over weeks. There is also a third possibility, one that excited theorists but seemed almost too perfect to be real. The coronal mass ejection impact might trigger a cryovolcanic event within the comet, a subsurface eruption caused by rapid pressure changes as volatile ice is sublimated faster than they could escape. If 3I Atlas contained pockets of pressurized gas trapped beneath a crust of refractory material, the coronal mass ejection could punch through that crust, releasing those gases in a directed jet. Such an event would be a natural experiment in high-energy astrophysics, a collision between stellar ejecta and primordial matter from another star system. Telescopes around the world were already pointing at 3I Atlas, watching, waiting for the impact. The data would be invaluable. But beyond the immediate scientific payoff, the event highlighted a deeper truth about space weather forecasting. The solar system is not empty. It is filled with objects, structures, and interactions that we are only beginning to understand. Coronal mass. Ejections do not travel through a vacuum. They plow through the solar wind, collide with planetary magnetospheres, strike comets and asteroids, and generate complex waves and turbulence that propagate across millions of kilometers. Improving space weather prediction requires more than just better model of the sun. It requires understanding the entire heliospheric environment, the ambient conditions through which coronal mass ejections travel, and the ways in which these transient events interact with everything in their path. Missions like a deep space climate observatory positioned at the LA1 Lagrange point between Earth and the Sun provide crucial early warning by detecting the arrival of coronal mass ejection shocks 15 to 60 minutes before they reach Earth. Future missions to the L5 point 60 degrees behind Earth in its orbit would give forecasters a side view of coronal mass ejections as they propagate, allowing for more accurate trajectory predictions. But even with perfect models and ideal observations, space weather will always carry uncertainty. Coronal mass ejections are chaotic, driven by magnetic reconnection processes that are inherently unpredictable. The orientation of the interplanetary magnetic field within a coronal mass ejection cannot be determined until the structure is measured directly by spacecraft. A forecast of G1 can become G4 if the B sub Z flips southward at just the wrong moment. A predicted direct hit can become a miss if the coronal mass ejection deflects around a high-speed solar wind stream. The long-term outlook remained ominous. Solar cycle 25 would continue producing powerful flares and Earth-directed coronal mass ejections for years. The baseline risk level had been elevated. Every coronal mass ejection launch carried potential for another G4 or G5 storm, another round of stress and failures. Resilience was now survival in itself. But the sun and its ejected plasma were not the only forces at play. As the coronal mass ejection raced toward 3I Atlas and Earth recover from its electromagnetic assault, another set of players was moving in position. The planets themselves, following their ancient orbital paths, were converging into geometries that occur only rarely, alignments that concentrate a gravitational influence and tidal forces in ways that can modulate energy across the entire solar system. Planetary alignments have fascinated humanity for millennia. Ancient astronomers tracked the wandering stars, the planets whose motions against the fixed background reveal patterns and periodicities. Conjunctions, oppositions, and syzygy configurations were recorded, celebrated, and sometimes feared. In the modern era, we understand these alignments through the lens of gravitational physics. Each planet exerts a tidal force on the Sun, on Earth, and on every other body in the solar system. Individually, these forces are minuscule compared to the overwhelming dominance of the Sun's gravity. But when planets align, when their gravitational vectors point in the same direction or reinforce each other in specific ways, the cumulative effect can become measurable. The critical alignment for our story was approaching on November 19th and 20th, 2025. The geometry involved multiple players: the Sun, Mercury at inferior conjunction, the Moon at new phase, Earth, and Uranus at opposition. Each of these bodies contributes to the total gravitational field experienced by Earth. And when they arrange themselves along specific axes, the tidal stress on Earth's crust and oceans reaches a maximum. The most important component of this alignment was the Moon. When the Moon passes between Earth and the Sun, we call it a new moon, and the gravitational pull of both bodies combines. This is when we experience spring tides, the highest high tides and lowest low tides of the lunar cycle. The Sun and Moon are pulling together, stretching Earth's oceans and even its solid crust in the same direction. The lithosphere rises and falls by centimeters in response, a slow breathing motion driven by external gravitational forces. The November 19th new moon was designated a micro-new moon, meaning the moon was near apogee, its farthest orbital distance from Earth. This reduces the tidal amplitude compared to a perigee alignment, when the moon is closest and its gravitational influence peaks, but the term micro is misleading. Even at apogee, the moon's tidal force is substantial, and when combined with the sun's pull during new moon phase, the result is significant tidal stress. Adding to this was Mercury's position. Mercury, the innermost planet, was at inferior conjunction, meaning it passed directly between Earth and the Sun. While Mercury is small and distant, its contribution to the total gravitational field is non-zero, and during conjunction, that contribution is maximized. Then there is Uranus, positioned at opposition, meaning Earth was directly between Uranus and the Sun. Opposition places Uranus at its closest approach to Earth for the year, maximizing whatever gravitational influence the distant ice giant can exert on our planet. The cumulative effect of this geometry is to maximize the total external gravitational stress applied to Earth during a specific 48-hour window. The tidal forces acting on the lithosphere, the crust, reach a peak. In most circumstances, this peak passes without consequence. The Earth's crust is strong, elastic, capable of absorbing these stresses without failure. But when faults are already critically loaded, when tectonic stress has pushed rock to the very edge of its strength, even a small additional force can be the trigger that initiates rupture. This is not pseudoscience or astrology, it is established geophysics. Tidal triggering of earthquakes is a documented phenomenon, particularly for shallow events in regions of high tectonic stress. The effect is subtle, a modulation rather than a cause, but in systems poised at critical thresholds, modulation is all that is needed. The alignment does not create earthquakes. It provides the final incremental stress that allows earthquakes to occur slightly earlier than they otherwise would have. The timing of the November 19th to 20th alignment was significant for another reason. It followed the electromagnetic triggering window. The G4 to G5 geomagnetic storm had struck between November 11th and 13th, injecting massive geomagnetically induced currents into the Earth's crust. Empirical studies of X-class solar flares and subsequent seismicity show a consistent delay of 7 to 8 days between the flare and the peak in earthquake activity. This delay reflects the time required for electromagnetic energy to couple into the lithosphere, to stress fault zones through piezoelectric effects and thermal expansion, and to bring critically loaded faults to the breaking point. Applying this 7 to 8 day delay to the November 11th flare places the peak electromagnetic triggering risk around November 18th to 19th. This window overlaps almost perfectly with the November 19th to 20th tidal maximum from the planetary alignment. The two effects, electromagnetic and gravitational, are temporally superimposed. A fault system already stressed by tectonic loading, then pushed closer to failure by geomagnetically induced current pulses, would face its final test during the tidal peak. The compounding of these forces creates a window of maximum vulnerability, a brief period when the probability of rupture is elevated beyond baseline levels, but this was not the only alignment on the horizon. Looking forward to January 2026, astronomers and orbital mechanicians identified another geometry of interest, one described as a superalignment involving Jupiter, Earth, the Sun, Mercury, Venus, and Mars. The centerpiece of this configuration is Jupiter's opposition on January 10th, 2026. Opposition places Jupiter at its closest and brightest position relative to Earth, maximizing its gravitational tidal input to the inner solar system. Jupiter is the giant of the solar system, containing more mass than all other planets combined. Its gravitational influence is substantial even at its average distance. during opposition, when Earth and Jupiter are on the same side of the Sun and separated by the minimum possible distance. Jupiter's tidal force on Earth reaches its annual maximum. This force is still small compared to the Moon's, but is not negligible, and when combined with alignments of the inner planets, Mercury, Venus, and Mars, the cumulative gravitational field can reach configurations that occur only once every several years or even decades. The January 9th to 10th geometry is significant, not because it will cause catastrophic events on its own, but because it represents another period of elevated tidal stress. If solar cycle 25 produces another sequence of powerful X-class flares in late December 2025 or early January 2026, and if those flares generate G4 or G5 geomagnetic storms, then the combination of electromagnetic triggering followed by the Jupiter opposition tidal peak could create another critical window. The pattern is clear. Space weather and orbital mechanics are not isolated phenomena. They interact through the common medium of Earth's geophysical systems. The magnetosphere absorbs energy from coronal mass ejections and transfers it to the ionosphere and crust through geomagnetically induced currents. The lithosphere responds to tidal forces from planetary alignments, flexing and straining under gravitational loads. When these forces converge, when electromagnetic pulses and tidal maxima occur within days of each other in regions where tectonic faults are critically stressed, the result is a compound hazard, a scenario where the whole is greater than the sum of its parts. This understanding requires a shift in how we assess geophysical risk. Traditional seismology treats earthquakes as internally driven events, the result of tectonic plate motion and stress accumulation over decades or centuries. External triggers are often dismissed as insignificant because they add only a tiny fraction to the total stress. But this perspective misses the crucial point. In a critically loaded system, tiny fractions matter. A fault at 98% of its failure threshold does not need another 50% stress to rupture. It needs 2%. And that 2% can come from external sources, from electromagnetic currents induced by space weather, from tidal forces during planetary alignments, or from both acting together. The November 19th to 20th alignment was not an astronomical curiosity. It was a potential catalyst, a temporal focal point where multiple physical processes converged to create conditions favorable for seismic triggering. Whether that triggering would actually occur depended on the state of the faults, the distribution of tectonic stress, and the specific details of how electromagnetic and gravitational forces coupled into the lithosphere. But the window was open and the stage was set, and the clock was ticking toward already a moment when the cosmos itself seemed aligned to test the strength of Earth's crust, and so all eyes turned to Japan. While space weather forecasters tracked coronal mass ejection trajectories and astronomers calculated planetary positions, seismologists were watching with growing alarm as the Earth itself began to speak. The message was coming from the northeast coast of Honshu, from the cold waters of the Pacific, where the oceanic plate dives beneath the continental margin in one of the most seismically active zones on the planet, the Japan Trench. The earthquakes had begun weeks earlier, a persistent swarm of moderate events that rumbled through the subduction zone with unsettling regularity. More than 30 earthquakes characterized the swarm off the northeastern coast of Honshu Island. Multiple magnitude 5.0 earthquakes, several magnitude 6.0 events, a magnitude 6.8 and magnitude 6.4 double strike. Each one was a crack in the brittle lithosphere, a sudden release of stress accumulated over decades of slow tectonic convergence. But these were not random background seismicity. They were clustered in location, progressive in magnitude, and ominously familiar in their pattern. The Japan Trench is where nightmares are born. Here the Pacific Plate, ancient and cold and dense, grinds beneath the North American plate at a rate of about 8 centimeters per year. That might sound slow, but over decades and centuries, it adds up. The interface between the two plates, the megathrust fault, becomes locked, welded together by friction and pressure at depths of 10 to 50 kilometers beneath the seafloor. Stress builds silently, inexorably, loading the fault like a colossal spring being compressed, and when that spring releases, the result is catastrophic. The 2011 Tohoku earthquake was a magnitude 9.1 monster, the most powerful earthquake ever recorded in Japan, and the fourth strongest globally since modern seismic monitoring began. The rupture zone extended 500 kilometers along the trench, and 200 kilometers perpendicular to it. The seafloor lurched upward by several meters in a matter of seconds, displacing an unimaginable volume of water and generating a tsunami that reached heights of 40 meters in some coastal areas. Over 18,000 people died. The Fukushima Daiichi nuclear plant suffered meltdowns. The economic damage exceeded $200 billion. But the 2011 earthquake did not strike without warning. In the 2 days before the main shock, the Tohoku region experienced a distinct foreshock sequence. On March 9, 2011, a magnitude 7.4 earthquake struck approximately 40 kilometers from what would become the main shock epicenter. It was followed within hours by 3 additional earthquakes exceeding magnitude 6.0. Seismologists monitored this activity with concern, but at the time there was no reliable method to distinguish foreshocks from ordinary seismicity. Only in hindsight did the pattern become clear. The fault segment was in its terminal preparatory phase, shedding stress through smaller ruptures as it approached total failure. Now in November 2025, the same region was lighting up again. The current swarm included the magnitude 6.8 and magnitude 6.4 earthquakes, along with 22 magnitude 5.0 plus earthquakes and countless smaller events. All were clustered near the Tohoku segment of the Japan Trench, close to the epicenter of the magnitude 9.1 Great Tohoku earthquake. The location was essentially identical to the 2011 precursor zone. The magnitude progression was similar, and most alarmingly, the focal depths were shallow, concentrated in the upper 30 kilometers of the crust, where the megathrust interface is locked and capable of generating massive tsunamis. Shallow earthquakes in subduction zones are particularly dangerous because they occur close to the seafloor. When a shallow thrust fault ruptures beneath the ocean, the overlying water column is displaced vertically with brutal efficiency. A 2-meter uplift of seafloor across a 100-kilometer rupture zone displaces billions of tons of water instantaneously, creating tsunami waves that radiate outward at speeds exceeding 700 kilometers per hour in deep water. As these waves approach shallow coastal areas, they slow down, pile up, and amplify, transforming into walls of water that can devastate entire cities. The question facing seismologists was stark and urgent. Was this swarm a repeat of the 2011 foreshock sequence? Were these events the final stress adjustments before another magnitude 9 megathrust earthquake? Or were they simply ordinary aftershocks from the 2011 event? A gradual relaxation of residual stress that would eventually die away without further consequence. Traditional seismology offered no definitive answer. Earthquake prediction remains an unsolved problem. The statistics of foreshocks are maddeningly ambiguous. Most earthquake swarms do not lead to larger events, but some do, and distinguishing between the two cases before the main shock occurs is beyond current capability. The best seismologists could say was that the fault segment was clearly under elevated stress, that the pattern resembled known precursor sequences, and that the hazard level should be considered high. But there was another perspective, one that integrated space weather and planetary mechanics into the assessment. This perspective came from a small but growing body of research suggesting that external triggers, specifically electromagnetic pulses from solar flares and gravitational tidal forces from planetary alignments, can influence the timing of earthquakes and critically stressed fault systems. The mechanism for electromagnetic triggering centers on geomagnetically induced currents. During a G4 or G5 geomagnetic storm, the rapid fluctuation of Earth's magnetic field induces powerful electric currents in the conductive layers of the crust. These currents can reach densities of 10 to the power of minus 8 to 10 to the power of minus 6 amperes per square meter, comparable to currents used in artificial pulsed power systems designed for industrial applications. When these currents flow through fault zones, they generate heat through resistive dissipation, alter pore fluid pressures through electrokinetic effects, and induce mechanical stress through piezoelectric coupling in quartz-bearing rocks. Statistical studies have found a significant correlation between X-class solar flares and increased global seismicity. Analysis of the top 50 X-class flares since 1997 showed an increase of up to 33% in earthquakes of magnitude 4.5 or greater within 5,000 kilometers of the subsolar point during the 10 days following the flare. Crucially, this increase is not immediate. The peak in seismic activity occurs 7 to 8 days after the X-ray event, reflecting the time required for electromagnetic energy to couple into the lithosphere and stress faults to the breaking point. Applying this empirically observed delay to the November 2025 sequence was straightforward. The X 5.1 flare peaked on November 11th. The G4 to G5 geomagnetic storm struck Earth between November 11th and 13th, injecting massive geomagnetically induced current pulses into the crust. Adding 7 to 8 days places the peak electromagnetic triggering risk window around November 18th to 19th. This window coincides almost perfectly with the gravitational tidal maximum from the November 19th to 20th planetary alignment. The convergence is not coincidental. It represents a compound hazard, a superposition of two independent external triggers acting on the same critically stressed fault system within the same 48-hour period. The electromagnetic trigger provides the first push, elevating stress levels and bringing faults closer to failure. The tidal trigger provides the second push, adding the final increment of mechanical stress needed to initiate rupture. For the Tohoku segment of the Japan Trench, which is already exhibiting swarm activity indicative of a fault at 98 to 99% of its critical failure stress, this compound triggering window represented maximum vulnerability. If any of the magnitude 6.4 shocks had further weakened the fault interface, if stress redistribution from those events had loaded adjacent segments, if pore fluid pressures were elevated due to slow slip or aseismic creep, then the addition of geomagnetically induced current stress followed immediately by tidal stress could provide the conditions necessary for catastrophic rupture. The United States Geological Survey maintains officially that no causal relationship has been demonstrated between space weather and earthquakes. This position reflects the conservative nature of institutional science and the high burden of proof required to establish causation in complex natural systems. But absence of demonstrated causation is not the same as absence of correlation, and it is certainly not proof of absence of effect. The situation in mid-November 2025 was therefore unprecedented in its convergence of multiple hazard indicators. a fault segment with a proven history of generating magnitude 9 megathrust earthquakes. A current earthquake swarm matching the precursor pattern of the previous magnitude 9 event, a recent G4 to G5 geomagnetic storm that injected massive electromagnetic energy into the crust, an approaching planetary alignment that would maximize tidal stress, and a temporal overlap between the electromagnetic triggering window and the tidal maximum that created a 48 to 72 hour period of compounded external forcing. Whether this convergence would produce a major earthquake remained uncertain. Earthquake rupture is a chaotic process governed by variables that cannot be fully measured or modeled, but the hazard level was undeniably elevated, the warning signs were present, and the clock was ticking toward the critical window. The Earth had been stressed, the cosmos had aligned, and the question now was whether the ancient fault beneath the Pacific would hold, or whether it would release its accumulated fury once more. The convergence was complete. Solar fury, interstellar visitors, planetary alignment, and tectonic stress had synchronized into a single critical moment in mid-November 2025. The physics was clear, the patterns unmistakable, the warning signs visible to anyone willing to look beyond the boundaries of traditional disciplinary silos. But what remained unclear was whether this convergence would transition from theoretical hazard to actual catastrophe, and more importantly, what could be done about it. The scientific conclusions were straightforward but sobering. Solar cycle 25 had proven itself to be significantly more active than predicted, producing sustained high-intensity space weather that was expected to continue until at least 2030. The G4 to G5 geomagnetic storm of mid-November 2025, confirmed by auroral sightings reaching as far south as Mexico and Spain, represented a baseline for the kind of extreme events that would recur with increasing frequency over the coming years. This was not an anomaly. This was the new operational environment for every technological system, dependent on stable electromagnetic conditions. The long-term implications for infrastructure were profound. Power grids, particularly those at high and mid-latitudes where geomagnetically induced currents are strongest, faced repeated exposure to transformer-damaging surges. Satellite constellations in low Earth orbit and geostationary positions would continue experiencing elevated drag, increased radiations exposure, and higher failure rates. Communication systems relying on high-frequency radio propagation would face persistent blackouts during X-class flare events. Global positioning system and navigation systems would suffer accuracy degradation from ionospheric disturbances. These were not theoretical vulnerabilities. They were demonstrated failure modes observed during previous solar maximum periods, and solar cycle 25 was proving to be one of the most intense cycles in decades. Resilience planning was no longer optional. It was essential for survival of modern civilization's technological foundation. The recommendations for space weather resilience were well established, but often ignored or underfunded power utilities needed to install neutral point blocking devices to prevent geomagnetically induced current flow through transformer windings. Grid operators needed real-time space weather monitoring integrated into their control systems, allowing for preemptive load shedding or network reconfiguration. During forecasted storm periods, satellite operators needed to design future missions with increased radiation shielding and autonomous safe mode protocols triggered by space weather alerts. Communication networks needed redundancy, alternative routing, and backup systems that did not rely on ionospheric propagation. But the more controversial and urgent recommendation concerned the integration of space weather monitoring into seismic hazard assessment. The correlation between X-class solar flares and increased global seismicity, while not yet universally accepted in mainstream seismology, was supported by statistical evidence strong enough to warrant operational consideration. The observed 7 to 8 day delay between flare occurrence and peak seismic activity provided a predictable window that could be used to elevate alert levels in regions with critically stressed faults. For Japan specifically, the situation in November 2025 demanded immediate action. The ongoing earthquake swarm in the Tohoku region, with more than 30 earthquakes characterized by multiple magnitude 6.0 events, including the magnitude 6.8 and magnitude 6.4 pair, combined with the recent G4 to G5 storm and the approaching November 19th to 20th tidal maximum, created a compound hazard scenario that justified elevated tsunami readiness recommendations. Included heightened surveillance of seismic networks with real-time data sharing, pre-positioning of emergency response assets in coastal communities, public information campaigns reminding residents of tsunami evacuation routes and procedures, and coordination with nuclear facility operators to verify that emergency cooling systems and backup power were fully operational. These recommendations were not predictions of inevitable disaster. They were risk mitigation measures appropriate to the level of hazard indicated by multiple converging factors. If the critical window passed without a major earthquake, the precautions would have cost relatively little and caused minimal disruption. But if a magnitude of 8 or 9 event occurred during the window, the advanced preparation could save thousands of lives through faster evacuations, reduce confusion, and better coordinated emergency response. The broader lesson from the November 2025 convergence was the necessity of interdisciplinary thinking and hazard assessment. Space weather, orbital mechanics, and seismology are traditionally separate fields with separate journals, separate conferences, and separate funding streams. But nature does not respect these artificial boundaries. The Earth system is coupled, interconnected, and responsive to forcing from multiple sources. Simultaneously, a geomagnetic storm is not just a space weather event, it is an injection of electromagnetic energy into the lithosphere that can influence fault stability. A planetary alignment is not just an astronomical curiosity. It is a modulation of tidal stress that can act as a trigger in critically loaded systems. An earthquake swarm is not just a seismological phenomenon. It is a signal of fault system state that must be interpreted in the context of external forcing. Future hazard assessment frameworks need to integrate these perspectives. Space weather forecasting centers should share data with seismological networks. Planetary ephemeris calculations should be cross-referenced with tectonic stress models. Earthquake early warning systems should incorporate inputs from magnetometers, monitoring geomagnetically induced current activity. This integration requires institutional cooperation, shared data standards, and researchers willing to work across traditional disciplinary boundaries. It also requires funding agencies to support interdisciplinary research that might not fit neatly into existing program categories. The case of interstellar Comet 3, Atlas, and its potential role in modulating solar activity highlighted another frontier: the need to monitor and study interstellar objects as they transit the inner solar system. These objects are messengers from other stellar environments, carrying chemical signatures and physical properties that may interact with our Sun in unexpected ways. If the correlation between 3I Atlas presence and the X-class flare sequence is more than coincidence, it suggests that the heliosphere is more sensitive to external perturbations than currently understood. Future observations of interstellar objects should include detailed plasma composition measurements, magnetic field monitoring, and coordinated solar observation campaigns to search for causal links. Looking ahead to the January 2026 super alignment involving Jupiter, the same principles applied. If solar cycle 25 produced another sequence of powerful flares in late December 2025 or early January 2026, the electromagnetic triggering window would overlap with the Jupiter opposition tidal maximum, creating another period of elevated seismic hazard regions with active faulting, particularly subduction zones, and transform boundaries under high tectonic stress should prepare for that possibility. The ultimate question raised by the November's 2025 convergence was philosophical as much as scientific. Are we passive observers of natural hazards, or can we become active managers of risk through better understanding and integration of multiple threat streams? The answer depends on our willingness to challenge disciplinary boundaries, to consider mechanisms that do not fit traditional models, and to act on uncertain but credible warnings, even when definitive proof is lacking. The Earth had been stressed by the Sun. The cosmos had arranged itself into geometries that maximized external forcing. The faults beneath Japan were showing signs consistent with their preparatory phases. The window of maximum vulnerability was approaching. Whether that vulnerability would manifest as catastrophe or pass quietly into history remained to be seen. But one thing was certain. The universe does not care about our institutional boundaries, our funding categories, or our comfort with uncertainty. It operates according to physical laws that couple systems together in ways we are only beginning to understand. Our survival and prosperity depend on how quickly we can learn those lessons and act on them before the next convergence arrives.